Hi everyone. Hey, Shao. Can you see me?
Yes, hey Aditya.
Hey, perfect. Thanks. So yeah, so let me introduce. Dr. Xiao Yang is our guest speaker today. He'll be talking about big data infectious disease estimation, which is very relevant to what we have been talking about in the class as well, students in the last couple of lectures from flu to COVID. As we all know, Professor Yang is an assistant professor in the School of Industrial and Systems Engineering. He just joined Georgia Tech, like most of the other people here. So I think he's still figuring out what kind of. So he might be, I'm sure, looking for students too. So if you're interested, you should ping him. He is prior to Georgia Tech, he was a postdoc in biomedical informatics at the Harvard Medical School. And in fact, he finished his PhD in statistics from Harvard as well. He's been working on data science for healthcare with special interest in big data, infectious disease prediction, and EHR records, right? And he has a lot of papers at very high impact places, including PNAS, PLOS computational biology, and so on. So we are very excited to hear about what his work has been. So Xiao, the floor is yours. And just a note of logistics, students, I would imagine let's put clarification questions as Dr. Yang is speaking, and then maybe more elaborate and technical questions can be kept at the end. And I'm sure Dr. Yang would be happy to give more insights or talk to you offline if you're interested. Thanks. Yep.
Thank you, Aditya. Yes, if you have any questions, and I'm actually currently actively looking for students, and if you're interested in what I do, please reach out. And I'm sure, I'm more than happy to have a chat. So speaking of that, I'm going to share my screen. I think I just checked that sharing screen seems to be working. Are you guys seeing my screen?
Yes, sure.
Okay.
We can see. Yeah.
Perfect. Then I'll get started. So yeah, as Aditya introduced, I'm currently in the ISYE of the Georgia Tech, and today I'll be talking about my journeys on the big data infectious disease estimation. Like Aditya, I've been working on infectious disease prediction, in particular flu and dengue for a long time. And recently, we're repurposing a lot of the knowledge that we learned on the flu to COVID-19. So I'm just here to share my entire journey on the from the very beginning. Probably we'll start in how I get into it and the history a little bit, and we'll see where we are right now with COVID-19. So that will be the roadmap of today's talk. Give a brief history of the flu prediction, including the CDC's effort starting in the 90s and the Google flu trends and its glory and subsequent unfolding of the story and our work. And I'll share three current paper we have on the COVID-19 in the later half of the talk. Using the LI net, some of the spatial temporal modeling, and the Google data. So yeah, let's get to the meat of the talk. Traditional influenza surveillance. I'm pretty sure you guys know this already. CDC have this ILI surveillance network. ILI stands for influenza-like units. So how it works is a recap. That's the participating hospitals around the United States send two numbers to CDC every week. One number is the total number of outpatient visits, and second number is among those visits, how many are having a flu-like symptom. CDC the aggregated number reporting on the national and regional level. What's the percentage of patients that is currently having a flu? And this number called percent flu is the gold standard for the current flu situation in the states for a long time since establishment in the 90s. The problem is that due to the time for aggregation and manual reporting, this number typically lags behind real time for a week to two. So that's clearly suboptimal. And entering into a digital stage, right? And right now, if you have a flu, before going to the hospitals, you probably search online, you probably tweet about it or write in the Facebook about it. So the idea is, given in the digital era, can we use all those online data for a faster flu detections, whether there will be an outbreak or not? So actually, that idea is first proposed by Google itself, and they call it Google Flu Trends. And that gives basically the idea and the promise in the big data era for the public health. How it works is that Google will aggregate their search query data and select out those flu-related queries and look at the volume of those and use those data to predict the current, call it nowcast, the current flu situation. So the left-hand side illustrates what Google can do, right? The black line is Google's prediction, and red line is CDC's estimate. And you can see that CDC's estimate is lagging behind real time for about a week or two, and Google's information is always available in real time. And the y-axis here is our prediction target, the percent flu, the percentage of people, outpatients that is having the flu, the gold standard. And Google actually published their paper in Nature back in the late 2008, early 2009, claiming that the search engine query data can indeed provide advanced information on the flu development. So people are really excited about this. Bear in mind this is 10 years ago, and this is probably one of the first few very splashing story on the using big data for something good for the public health. And they actually made it to the front line of the New York Times, right here. And if you look at their retrospective comparison, they are doing pretty well in terms of in-sample prediction, fitting of the data. So you can see that the ground truth and the Google prediction. Google prediction is the yellow, ground truth is the blue. They kind of correlate well with each other. And they have an interview with New York Times and suggesting that this could be the opening up new doors for flu predictions. And things are all well here. And the natural next step for Google is to publish their result in real time, right? So that it can be used for for resource allocation during disease time. Pretty much like what we have right now, that different research groups publish their predictions for the COVID-19 in real time so that people can get better prepared. And that's where things fell short. And if you remember, they published their paper in late 2008, around 2009. So what happens in the early 2009 here is that immediately after the publish of their Google flu trends, they underpredict the first off-season flu that we haven't seen in a long time. The 2009 is a swine flu, and Google basically underpredict what's the CDC reported number. CDC reported number by more than 50%. And this is because 2009 is an off-season flu, the swine flu, H1N1. And your typical flu happens during the winter, from the November to around May time. But this swine flu, off-season flu, happens in the spring and the summer. And that's completely because the Google search queries haven't seen all those off-season flu, it failed to capture it. So that raised the skeptical on what's the efficacy of Google flu trends. And when things like this happen, which what Google did, and like all of us will do, is going back to the drawing board and recalibrate their model. And they recalibrated their model, have an algorithm update. Things are pretty well for the subsequent 2 years. Until the third year, in 2013, where Google overpredict for another 100%. This is because in 2013 there's no off-season flu. 2013 is just a regular flu season, but having a pretty high flu outbreak. So media start to report about flu, and people are searching for flu information, even if they are not getting the flu. So Google saw a surge in the search queries related to flu, and mistakenly thought that everybody is getting the flu. Thus, a big overestimation of the actual flu occurrence. Like the old saying goes, "Fool me once, shame on you. Fool me twice, shame on me." At this time, people no longer trust Google. And the media reports about the Google's failures flushing the internet. I'm just picking a few headlines here. So the story finally winds down by Google shutting down their Google Flu Trend service in the August 2015. They will no longer publish the real-time estimation of the flu situation. So what went wrong is just, from this history lesson, is just digital disease detection. That there just big data failed? Now, to answer why Google really failed, we have to look at the model behind Google Flu Trends. The engine under the hood is incredibly simple. In their Nature paper, and they published their model to be a univariate, basically univariate linear regression, where they have the target data, target truth is the logit P, where P is the percentage of people having the flu, right? Percentage of patients, all patients having the flu after logit transformation. And Q is the friction of flu-related queries, total volume, divided by the entire volume after logit transformation. And that's it. One response, one predictor, a linear regression. And once they train the model, they keep the model static and do not update for another 2 years. So that naturally raises the question about, where does this 45 search queries come from? If you dig out the supporting information of that original Nature paper, what we find is that this figure, right? They say that they identify the top 45 queries by correlation of the search volume to the flu intensity, the percent ILI activity. And we don't really know what are those 45 queries, but we do know that they consider something like Oscar nomination in their top 45 queries. It's a little bit baffling because Oscar nomination really have nothing to do with flu, right? So why is it even considered? Well, although Oscar nomination has nothing to do with flu, it has everything to do with winter. You see, flu tends to occur during the winter, and Oscar nominations happens in the winter as well. So if you're only looking at the marginal correlation between Oscar nomination and flu activity, the marginal correlation is actually pretty high. So that suggests that, although we do not know what are all those 45 query terms, there could be, spurious correlations or terms identified by Google. And that's why in the early stage, it failed to capture an off-season flu because it's so overfitted to seasonal flu. And some is even, half-jokingly saying that Google is predicting the winter rather than predicting the flu. Right? So, we don't know which. So a few implications from Google's failure will be the model static, meaning that they train the model, they use it once for all. It's not an online learning where you try to adapt your model based on every week of data, which we know that currently that we should do. And this is particularly troublesome in the search queries because people's search pattern changes. So does Google search engine. In the very early days, if you try to do Google searches, you have to type in the entire search phrases that you want. Right now, you only need to type in part of it, and Google will give you suggestions on what to search. This, of course, will change people's search pattern, and a static model cannot capture that. And a second implication, a lesson learned, is that they aggregate multiple queries into the single variable Q. Basically, they use total volume of these queries. This effectively places equal weight on each of the queries, but we know that some queries could be more important than the others. And third one, pretty much related to the first, is that during the flu season, CDC actually have the flu report update, pretty much like what we now have COVID-19 case update every day. Back then, CDC have case update every week, and a reasonable model should incorporate those crucial information. However, it's not used by the Google Flu Trends. And lastly is that the flu activities, or in general infectious disease activity prediction, you are predicting a time series. But in Google's model, you can see a simple correlation between the volume and the target. There's no time series information used, and that is a huge loss of information. So all in all, it just seems to suggest that we need a new statistical method. And in particular, Google discontinued their efforts in 2015, and that's why we feel like academia and researchers should carry on the idea is neat, right? We want to carry on the mission and just do a better job at it, and that's where we propose our own model. We call the autoregressive with Google data that's trying to address all those issues. Before I go into our model, any questions on the little histories on Google Flu Trends? All right. Then I'll introduce our model. Right, this is a pretty early stage, our model introduced in 2015, that we are basically trying to add the search verb, just address the shortcomings of our original Google Flu Trends. We are using individual search terms as opposed to lump them together, right? And we are using the same target as Google. And we are investigating the data generating mechanism, basically draw a diagram that the Y evolve according to AR, autoregressive model, X evolve according to, only depends on Y, capture some causality assumptions that the online searches are in response of the flu occurrence. And in the end, we have kind of not a hidden Markov structure, but feels like it's really a delay reviewed Markov process, where you have the Y involved in time, and Xn only depend on the current Y, and you will only know Y for the historical Y, right? Not knowing the current Y. So it's like a delayed reviewed structure, but with this type of causal diagram. So with this, we can employ a Bayesian paradigm trying to work out what's the predictive distribution. And it turns out to be a linear combination of past lags together with the Curie terms. So that's why we put it together as a type of a linear model. And in the model training, we select k equal to 100 terms from the Google Trends. That's the top 100 terms that we are getting. And we select n equal to 52 weeks, basically an AR52, to look at all historical lags to see what are the lags that might be useful. And we use a 2-year rolling window to capture the latest data. And because we have more predictors than responses, we want to use the L1 or L2 penalties on the model coefficients alpha and beta. All things very natural, right? And in the end, we just have a giant loss function that we are trying to minimize with L1 and L2 penalty. In practice, we actually find that L2 penalty is not that useful, so we even zero that out, make things even simpler. So that's our little model. Very simple and intuitive, and it captures the dynamics. So this is the model in action in terms of prediction results. You can see that in the 2013 year, we are doing a reasonable job while the Google actually overshoots to the roof. So why, how are we addressing all those shortcomings of the original Google Flu Trends, and why do we believe in that the model should have a reasonable performance? Right, a few features, right? Because we dynamically train the model with a rolling 2-year window, so whenever the new CDC reports become available, we'll retrain the model, and it basically gives the model a sense of self-correcting, right? A lot of the teams with COVID-19 do the same thing because things are so fast, things are so fluid and fast evolving. For example, I'll give the year of 2009 and 2013 as an example of why dynamic training, online learning is important, right? So in 2009, you can see that we are picking up the first peak of the H1N1 flu, the first wave, but we are underestimating it. So that in the second week, the dynamic training of the model basically dynamically allocate weights between the Google search terms and the time series terms. So more weight is allocated to the Google search terms in the second week, so that the model becomes more responsive and captures the indeed, what is happening on the second week of the H1N1, and that's a kind of a self-correction in that domain. And conversely, in the 2013, what we already know is that here we overpredict after the peak. The Google terms are actually over-predicting the actual flu occurrence due to all the media reporting and so on. So in the second week, a dynamic training will shift weights from the search queries back into the time series component, so that in the second week is self-adjusted, so that we do not have a.
我看到那个弹哑了，你看到吗？
Hello?
Hello?
Sorry.
It's fine. Yeah, it's
Yeah,
probably
sorry.
a muting issue.
Oh, okay. Thank you. Sorry.
Yeah, I don't know. Probably one of the students. Let's see. Oh, yeah.
Yeah, I think that's what happened. Sorry. Yeah.
Okay, that's fine. L1 penalties. L1 penalty is important because we're kind of lazy. We want the data to tell itself, what are the time series lag. That is important. And L1 penalty also gives some sort of flexibilities in terms of incorporating the seasonality of the seasonality information, going back all the way to 52 weeks into the time series prediction. So if you look at the data, right, visualize the data, you'll realize that the actual flu occurrence, the black line, exhibits strong seasonalities. But it may not be exactly 52 weeks. Sometimes it's 49, sometimes it's 53, and using the penalized L1 penalty with a lag of 52 basically allow us with such flexibility. And we also penalize on the search volume data to basically automatically select the most useful search queries for the estimation. And here's a heat map of what is selected. Right? Out of the top 100 most correlated terms with the flu activities, only a few are selected, such as fever, cough, breaker fever. Similar exercise exists for COVID, right? There's a lot of information. People search for a lot of terms during the COVID period. What are the terms that is most correlated with the COVID cases? L1 penalty is going to give us some insight into that. And the 2-year rolling window gives dynamic fitting. That is basically a very elementary attempt, for an online learning type of exercise where you try to readjust the model so that it only incorporates the most recent information. So overall, we just compare, what the result we get with the Google Flu Trends, and the result is very reasonable. And we didn't stop there. We are actually comparing with a few more methods, such as, how about the lasso on Google data only? How about the AR3 model just as a time series based model? How about the Google Flu Trends plus AR3 to see how optimally aggregating the information could help with the prediction exercise, right? So this overall just gives more insight what is shortcoming of this type of approach and what is the strength. For example, if you look at a table summarizing the accuracy metrics, you'll find that our model during the whole period, is better in terms of mean absolute error. So error metrics, the time series components are in general better than the Google information. It's just because Google information can tend to be noisy, and time series give you a kind of a nice smoothing result that is going to overall help with the prediction error. However, if you look at something called correlation of increment, right? This is kind of like a martingale correlation. You look at how responsive is one predictor to the actual flu up and down, right? You look at the increment. You'll realize that, in terms of increments, the Google information is actually doing a better job prediction of the increments than the time series approach. So this suggests that time series approach, although smoothing, is a trend-based approach, is accurate, but tend to have a delay in response. So what we see here is that our model, called Argo, combine the two is actually a compromise of the two, and it's always giving kind of best results in terms of mean square error and also the correlation of increments. Decomposing into different seasons, and especially the off-season flu, you'll see that we are still having, if not the best result, will be the second best result. The red basically shows the best, and the blue shows that shows our method when our method is the second best. So very simple ideas and very intuitive, and not a very complicated method. We published the paper in the PNAS, and it was well received, and I'm personally very glad to see that Google itself actually published a blog in 2015 saying the next chapter for Google Flu Trends will be handed over to academia, and they basically highlight our group to see the contributions that we have on the using the Google search queries for flu prediction. I'm pretty happy to see this, and of course there are some other media coverage of our efforts, just to flash a few. And we didn't stop there, right? The next is how can we further improve, right? It's big data, and big data is not necessarily restricted to search volume. How about electronic health record? Actually, that's how I get into the whole business of electronic health records. So it's not only electronic health records, it's cloud-based electronic health records. So basically like AWS hosted EHR, and we can get some kind of aggregated information in real time or in near real time. And we're basically predicting 4 weeks into the future using an aggregated, cloud-based EHR information with the Google search information. And we're broadcasting our results in real time. And we summarize the results we have in the BMC infectious diseases. And another effort is, okay, we can do it for flu. How about other disease or other countries, right? So we look at dengue trends, dengue fever for Brazil, Mexico, Thailand, Taiwan, Singapore, basically tropical countries. And we're able to show that, for example, for Brazil, this is what we are able to do. We're predicting the dengue occurrence case counts 1 month ahead of the official dengue report. And the pink area is we also have an arrow band associated with the method. So, that's the journey we have so far. That's all on the national level, right? Predicting the disease occurrence on national level. We know it's useful in terms of, speaking internationally. But if we're looking at U.S. itself, right now, COVID, right? People care about COVID overall occurrence, but we care more about all those infectious diseases that are near us. So naturally, we need to zoom in to a finer spatial resolution. And it's great that CDC actually have this information for 10 regions of the US. So entire US is divided into 10 HHS regions. I'm pretty sure that TDI already covered this a little bit in the courses. For example, the first region is New England, traditionally known as New England, covering the 6 northeastern states. So what we want to do right now is, in addition to predict the flu occurrence in the entire nation, we also want the flu occurrence in each of the region of the US. So our prediction target becomes instead of a single regression, it becomes a multitask regression, right? You're having a 10 vector as the response every week. So we've been looking around, and surely we can apply the same model that we propose on the national level for each region's data individually and independently, and we'll get some estimate. But clearly, this type of approaches will overlook the spatial correlations across different regions. For example, this picture illustrates how much spatial correlation there is across different regions. The thicker the line, the higher the correlations between the flu occurrence. For example, a central region like region 5 is having a very strong correlation in the, I think, Chicago area with its neighboring states. So that prompts us to say, okay, we probably do not want each region to have its own independent data model. What we want is actually have all of this, a single pooling of information across 10 different regions. And if you think about it, we can do even better, right? In addition to this, we can also have a national level result. So it's a pooling across geographical areas and also pooling across resolutions. We want this pooling to do all these tricks. So that's where we kind of summarize what a good model for a high resolution prediction should incorporate. It should have some spatial structure. It should have some temporal structure, and it should incorporate multiple resolutions. For example, state level, region level, national level, regional level, state level, and even county level and city level. We'll cover that a little bit on the COVID part in our method. And we want the data to be multi-sources, right? We want the Google search data together with the CDC data. So that's where we propose our kind of updated results. We simply call it Argo 2, just a follow-up, call it two-step augmented regression with Google data. Still a very simple linear approach, right? Trying to capture the generating mechanism, trying to capture the intuition behind. So how it works is, in our first step, we will train model individually for each of the region, and for the national level using different each individual region will train the same model but trained completely independently with their own data. And the second step, we do a pooling. And that's basically a nutshell of what we are going to do. So a little bit closer. Step 1, what we do is actually, a Argo on the national level, the same model that I just introduced. And for each of the region, right, if I blow up one particular region, you see that it's simply a lasso approach. where we try to regress the response to the search volume data. And after that, I kind of have an aggregation, like a projection of like a dimension reduction of the different regions search volume into a univariate vector that is projected onto the region's own flu activities. And why we are using each region's Google projection individually? This is because linguistic is a really interesting thing, right? People can talk about in terms of different terms, but referring to the same thing. And we're trying to incorporate that heterogeneity in linguistic into account. For example, this is a very fun map I find on the internet. So this is actually how different people refer to a carbonated drink, right? People can call it either a soda, a pop, or a Coke. So New England and California, people call it soda. Northern part of the country, call it pop. Southern part of the country, Atlanta here, we call it Coke. Even if it's a Sprite or something. That's just very interesting to show that people in different regions can call the same thing in different terms. And in the context of flu, this is actually a search intensity. More people search for flu in the northern part, but more people search for fever in the southern part. So training the search volume data individually, like a projection individually for each of the region, accounts for such linguistic heterogeneity.
So quick clarification, Shihao. So do you use the same set of terms for the entire?
Same superset of terms. We have around 129, but then use an L1 penalized projection to figure out what are the terms that is more useful for each of the region.
Okay, got it. Okay, thanks.
Yeah. So after step 1, what we got is a national level prediction, a Google data only, like a projected value summary of a dimension reduction of the Google data here. And then we have the regional kind of a vector time series of all the past legs. In the step 2, we want to basically aggregate them. So if I open up this pooling of information, I have my input of 3 different inputs. I try to predict one single output. I again have a Bayesian motivation. Basically, I'm basically aggregating 3 pieces of information and trying to do one prediction. What I do is I look at the generating mechanism, having some data generating mechanism assumptions. I look at the increment. So basically become instead of an AR, I look at the integrated AR increments involving vector autoregressive. And the first step results are all independent information. So basically I have a conditional independent structure that I look at, the national predictions and the Google Trends predictions are all unbiased and independent predictors for the current flu situation in each of the region. And the increments is evolving like an AR model. So I aggregate all those information. It basically becomes a precision matrix weighted average of each of the 3 components. So think about it as, I just use a weighted average of these 3 components to predict the current flu situation in each of the region. And the weight is a matrix weight, precision matrix weight. And turns out we have a best linear predictor with some structured covariance matrix. We try to employ some kind of ridge regression type of regularizations on it. And we use our familiar dynamic variance estimation with the rolling 104 weeks to capture the latest development. So that, we have basically a best linear prediction type, conditional estimation type of estimate together with a 95% interval. And, that's the nutshell of it. The features include inherited from our original Argo. Now we have dynamic fitting, automatic query selection, seasonality, and all that. And we have new features of spatial temporal correlation, multi-resolution information, and flexibility to incorporate other information in this kind of precision matrix weighted average, very classic framework. And the result is very nice, actually. We are able to see that our Argo tool, relative in each of the region, is outperforming the benchmark models like vector autoregressive GFT and GFT plus vector autoregressive model. And what is very comforting for us is that the coverage of our 95% confidence interval actually have an empirical coverage of 94.96. This basically says that our quantification of uncertainty is really on the spot, meaning that our structure of the variance covariance, data generating mechanism seems to be all very in line with what's actually happening in the real data. So that's very good. And in conclusions, we have Argo tool for the national, regional, and we actually have it for the state level Argo tool as well. Same kind of good performance. And the Argo summary a little bit will be looking at search volume data and time series data. Time series data is kind of smooth and have seasonality, but have a delay in action because it can be over smooth. Google search informations can be sensitive, very noisy, overshooting to the roof if there's any outbreaks. But but it could have been responsive. Although it can overreact, but it can be responsive. The Argo tool is basically a spatial temporal pooling with multi-resolution information that take the best side of the world. And the dynamic training online learning is going to be important. That captures the search engine changes and people's pattern changes. Back then, we were proposing some future works in line of all this, going to the municipal level and all that, until COVID-19 basically break out. And we are immediately thinking, can we basically apply the knowledge that we learned on the flu side onto the COVID-19 prediction? What are the insights that can be borrowed, and what are the model can be repurposed for COVID-19? Right? What are the limitations? It also shows limitations, which I will honestly disclose in the second half of the talk. But so far, any questions on the flu side before I transfer to the COVID-19?
So I had one question, Shihao. So very nice work, and especially I was wondering, did you see any differences between using this for dengue compared to, say, flu?
Yeah.
Were there was it just a matter of just change the terms and that's it?
Using dengue and using flu changes the terms, and the penalty actually changes slightly. In dengue, we'll find L1 and L2 penalty to be important, and cross-validation is going to be a more intensive exercise. And also, we find that in dengue, because the regions are less developed, for example, in Singapore and Taiwan, the internet penetration really become a thing. There are more weights on the search terms, and compared to Mexico and Thailand, actually the search term is really there just to help with the trending, the time series information. So there are times that where the searches is actually playing a dominating role, and the time series is there to help with the smoothing. But for the less internet developed country, it's actually time series is playing a majority of the role, and the search is really there to give a hint.
Great. So that's very interesting. So I mean, as a researcher who is trying to do this, like for the students, I was just wondering, how would they? Do you relate it to the epidemiology of the disease, or this is more like trial and error? That's how you find out that this works better.
I think I'm not sure about the epidemiology of the disease. I think if you refer to different type of diseases like flu or dengue, because of the model we do not have a mechanistic assumption like SEIR model or something like that. I think we are more kind of robust to the type of disease. We are more sensitive to the internet penetration. We are more sensitive to the internet coverage. So we are more sensitive on the big data generating part rather than the disease kind of evolvement side. That's what I find. It doesn't really matter it's dengue or it can be another diseases, maybe yellow fever. I don't know. We do not have assumptions on how different diseases evolve. For example, dengue is mosquito-borne disease, and flu is like human-to-human transmission. But we do not find much of a difference over, the mechanism why they kind of disease spread.
Great. Yeah, thanks a lot. I think that is useful for the students to hear, because we have been doing a lot of modeling, and obviously for each of these mechanistic models, each disease has its own specularities, right? So data-driven methods can give you a different perspective. Yeah.
Very different perspective. Actually, I'll talk about a little bit on COVID-19. We're recently trying to merge the two, because this is really two very distinct school of thoughts, and there's not much in the cross-section of the two, which I'll touch base a little bit when we talk about COVID-19, because you can see two school of thoughts in the COVID-19 prediction as well. So entering the COVID-19 pandemic, I'm going to, again, sketching through a few of my current work that is trying to predict, well, not all of them are predict, trying to study the COVID-19. I'll give a work for early stage surveillance, a work that we actually published in late April on the pandemic spread. And I'll have another work that we recently submitted for spatial temporal modeling, spatial structure, and also share with my personal struggle with the Google search information. I'll honestly disclose what is really, the challenge there of search volume, big data for a novel disease. So in the very early stage of the in the early stage of the COVID-19, back in March, what we realized is that a lot of you probably already realized early in March, there are a lot of people getting a flu-like symptom, such as fever and all that mild symptom. It turns out to be associated with COVID-19 instead of flu. So back then, the CDC's LI-net is still operating normally, like half normally, and we see another spike in the influenza-like symptom. And what is influenza-like symptom? Really, is a fever and a cough or a sore throat without a known cause rather than influenza. And back then, actually, the novel coronavirus fall inside this LI criteria. So if you examine the data of CDC LI-net, reporting how many people is actually having this type of fever, sore throat, runny nose type of symptom, you will realize that in the March side, there is a third spike where my mouse is at for the LI. Typically, flu only has two spikes, right? It's an influenza type A and influenza type B. But here is another spike. So our hypothesis back then is that most of the cases that you see here with mild symptom probably is associated with COVID-19 rather than flu. In fact, this is a screenshot, a very early stage of the CDC website. You can see that the LI-net is actually under the COVID data set. This is because the folks at CDC actually realized this already. And what they're trying to do back then was, okay, can we use this year's ILI, contrasting with last year's ILI, and try to figure out how much of this third spike is related to COVID-19, like a temporal control. And we're thinking about it, okay, we have this big data, right? If I can use big data, alternative source of data, to estimate this third spike, how much actual flu is having, how much actual flu activity there is in the third spike, I can take the difference, and the difference will be associated with actually the COVID-19. So that's what we did, right? Okay, this is a nice chart that you show in in this year you have a third spike, whereas last year you only have two spikes, and the year before last year you only have two spikes, 2018, 2019, this is 2020. So we're trying to figure out how much of this third spike is associated with COVID-19. What we do is we're actually having this pharmacy prescription sales data. Now we know that there are certain drugs that is only prescribed to deal with flu, not COVID-19. So what we do is look at the history of influenza activities based on the pharmacy sales, electronic pharmacy sales data, and fit it to the LI activity. And looking at, the feeling is reasonable for all the past years. And looking at the February 2019, there's a huge discrepancy between the LI activity reported by CDC and the prescription drug that is falling down. So basically, what we say that this difference is our estimated association with the COVID ILI that is associated with the COVID-19. And we actually estimated this factor, to be around 10 times towards the end of March 2018. That is, reported cases back then is only 85,000, and we are estimating around 700,000. And later on, based on the serology data, right? Later on, based on the serology data in July, August, we know that the under-reporting bias is probably a factor of 10, which is very much in line with the insight we get in early April. And this paper is actually published pretty early, published in May, and accepted in the late April already. So in the clinical infectious diseases. That's one of the work we do, leveraging our knowledge on the influenza-like illness and the symptoms of COVID-19 and the kind of big online data that we have access to. And another work we do currently is trying to use kind of spatial temporal modelings for the COVID-19 pandemics. What we know from the Argo and Argo 2 is that spatial temporal structure is very important information that we want to utilize. And penalized regressions can be a promising way to capture the dynamic in the data. And we also know is that the finer you go, right, the more insight and the more kind of actionable, the more interventions that can be taken. So, we are here, this effort, we are trying to predict for the following next 2 weeks, the COVID-19 cases and deaths, confirmed cases and deaths for each county in the United States. So our response response variable is of a dimension of 3,000. We're looking at 3,000 counties in the United States and trying to predict them jointly. And the information we use basically is, the mobility data, the past confirmed cases, and death information. And the diagram we basically use is basically a high resolution, high dimension spatial temporal model, spatial temporal regression, that we are trying to incorporate different types of correlations that there may be. For example, we are proposing 10 different transportation hubs in the United States by looking at roughly the airline traffic data. And we are proposing looking at different neighborings of counties by looking at the highway traffic map. Basically, from the map, we kind of get a connectivities between different counties and use that connectivities as a structured variance-covariance matrix in this kind of penalized approach. And the result we get is pretty promising. We are able to predict, deaths in different. This is aggregated deaths from different counties onto the state in a reasonable accuracy, and we are also able to read out the coefficients in the model. So it's really an interpretable model where we know that, okay, when Atlanta is having a spike, where else in the COVID-19 cases or deaths, where else is more likely to spread it to, right? It turns out to be Atlanta area. If Atlanta is having a spike, maybe later on you have a New York area, Florida area, and the Seattle area. So that's all basically being reviewed by the data. We also look at, we also have demographics data in this type of prediction. Now we know that even though for some counties there will be more cases shooting up, but we are predicting very few deaths because some counties are very young. They have a big population of young people, and we can actually read out those coefficients from the model, and it is really interpretable. This result is currently under review. And we have an archive version that is available. You can, I'll invite you to take a look if you are interested in our approaches. This is joint with Yao and some of her students. And after that, any questions so far on the two models that I introduced before I get into my struggle with Google data? Okay, now it's time to share some not so successful story. Since it's a class, I think it'll be good for you to know, there are struggles in research, for sure. So the Google searches is intuitively, it should be useful, right? It should be a short-term signal. I know it's already sensitive to media coverage. And in the COVID stages where, initially people have no clue about what it is, it's just having this kind of huge confounding bias in the data. So here's a few plots that I try to generate. This on the left-hand side is the national new cases, new death as of July, right? And on the right-hand side is the search volume. You can see very interestingly, search volume shoot up really, really fast. and then shoot down also really, really fast, much faster than what the cases actually is. The case shoot up exponentially, but decay very slowly. But the search is really kind of, like a, how should I call it? It's really, hotness. It's really hot around this period, and it has a very short-term memory. And people search for it, they know it, and they just move on and do not search anymore. And the search volume just drops so quick. And there's also huge confounding bias on this spike. But there are also terms that we know is useful. For example, there's a second peak during the summer, right? And so we can see that the search volume data is picking up this small tilt. But interesting enough, the second peak in the confirmed cases is actually much higher than the first peak. But in terms of search volume, you can see that the search for fever is much higher during the March compared to during the July part. So that means the relative magnitude, it can only pick up trends. The search volume, the relative magnitude in the search volume do not necessarily represent the relative magnitude in terms of cases. So that's another challenge that it can only use to capture trends. Is it going up? So another thing that is really interesting is that the search volume seems to have a kind of, if you have a 2-week kind of a lag ahead information compared to the actual cases. So this is a smoothed out version of the cases and the search volume. You can see that if I lag 0, it looks like this. If I lag 1, it looks like this. Lag 2, it now becomes pretty much on top of each other, but it's decreasing much faster. So there are informations definitely inside the search volume where we can use that information for prediction. It's just that the information is very noisy, not in the sense of noise, but in the sense of have so much hidden confounding factors that it's very difficult to separate the searches from those who actually have the symptom compared to searches of researchers, how their searches relative, in response of news and all that. We also look at the media coverage of the COVID-19, how many articles about COVID-19 is published in the media every day, and trying to kind of separate the search volume data with the media coverage data. So there are things we are trying to do to mitigate the effect, but so far, really, you can see that a long-term kind of 1-week prediction is okay. We kind of have an error reduction of 70%. But as soon as we are going to the second week or beyond, the prediction accuracy is not as good as what we wanted. The national level, I think, is probably okay. But when we go to state level and county level, the search data becomes even more sparse, and there are even more challenge utilizing the search volume data for the COVID-19. Right now, we are still working on it. We're trying different methods, and of course, we're trying Kriging, Gaussian process, nonlinear methods like that. But still, it's quite a fundamental issue with volume, with search volume data. That maybe as the COVID-19 becomes more and more, call it regular, is no longer that novel. Right now, people have a lot more knowledge about it compared to March time. So I was thinking that once it becomes something that people get to live with, then the search data probably will become more and more useful for a prediction exercise like this. Well, I think I'm almost up on my time. That's good. Just have some final remarks that I always want to share when dealing with big data. Right? I'm not really an infectious disease expert, but then really know the online data, big data. So the big data really present a great potential for infectious disease tracking, as an application of big data. But it's not really the size of big data that matters. As you can see, that Google failed in its flu in its first attempt, and we are currently struggling with using the Google data for COVID-19 prediction. So really, the successful work we have, on the flu side, on the dengue side, on the COVID side, is really all about asking the right questions, using the right model, and applying the right statistics. That is all that makes a difference, right? And I especially like this quote, and I want to share with all the students here, is a laser from the aftermath of Google flu. a science paper, actually a commentary, a formal paper that commenting on the science on the Google flu. It says that this quote: "The quantity of data does not mean that one can ignore the foundational issue of measurement, construct validity, and reliability and dependency among data." So just I want to end my talk here with this final remark, and probably we have 15 minutes open up for questions.
Great. Yeah. Let's thank Shihao for that nice talk. So I don't know if you can hear everyone clapping. So great. Yes. Great. Thank you. So yeah. So any questions for?
I have a really brief question.
Mm-hmm.
Oh, yeah, sure. Go ahead.
Yeah, so I was wondering if, given that the current data on COVID-19 is really noisy, as you say,
Mm-hmm.
is there like any available data on seasonal like coronavirus so that you can use to adjust your model?
We are actually very interesting question. Well, right now, one approaches that we are having is trying to build a model for the. So it's really interesting. It's a challenge. I'm talking about SER model and the data science data-driven model, right? So if it's more like an SER model, I can use the SER type of dynamics using the signal data to train my mechanistic model parameters and maybe keep some of the like R0 and those with scientific interpretation for a COVID-19 prediction. However, for data science, for data-driven approaches, for the COVID and for flu, first of all, there's no seasonal coronavirus. To my knowledge, there are seasonal flus. We are trying to use information from seasonal flu to calibrate the model for the COVID-19. However, it's difficult because then the search volume and the searches are very, very different, much more different than they're much more different than mechanistic model. I can imagine. I actually talked to someone. There are parameters you can borrow from the SER models, in the calibration exercise from flu to the COVID, but there's not much that we can do on the coronavirus with respect to the Google data. There are things we can borrow. For example, when we do spatial temporal structure of the data, I can use flight information, highway connectivities, and all that, and maybe use seasonal flu kind of correlation to have a spatial structure as a baseline spatial structure to operate on top of it. But in terms of Google searches, it's really a challenge.
Thank you.
So I had a question. So I think given the sensitivity which you talked about for COVID, right, in terms of search terms and media coverage, so then so when you compare this to your like the high resolution model which you talked about at a county level, so how do you see that? So there you didn't use the terms then? I
Didn't
guess?
use this. I
Okay.
didn't use.
Okay.
That's why.
Interesting. Cool. So the other thing I had in mind was like, so how sensitive is it to the set of terms you start out with, right? So and how do you go about deciding it? So like somebody gives you that, or you have to actually sit.
I spent a lot of
about...
time creating that. Previously, Google have a service called Google Correlate, where you can upload a time series, and Google Correlate will return you top search queries that is most correlated with the uploaded time series. And that service has been decommissioned in December 2019. So right before COVID, they decommissioned a very important research tool for identifying query terms. Right now, the query terms is really a kind of like research group brainstorm together and asking epidemiologists and interview with people to get a superset of the terms and look at the correlations and variable selection approaches. But there might be some other terms that are just escaping from my attention. It could be a serious.
Interesting. So you don't have so I'm guessing then you focus more on terms which make sense, right, from an epidemiological setting than random spuriously correlated terms.
Of course. We are now we started actually with all the flu related terms and just do a regular expression where you substitute all the flu-related queries terms in the queries with coronavirus or COVID-19 and all that, and get the superset and then do a variable selection.
Interesting. Cool. Yeah, I mean, so data-driven work also involves a lot of, so that is important for students.
Yeah, that is important for sure.
Yeah. Good. Any other questions from students?
Yes.
So I guess I'll put out the links about the papers which Shihao talked about. That will be on the course website. So yeah, you can also read that.
Yeah, I will also share this PowerPoint afterwards, so you can review, and also I put the rest here.
Yeah. There was someone asking a question, I think. Who else?
Yes.
I have a small question.
Okay. So maybe one of you can go first.
Okay.
Okay, Jiaming.
Jiaming, you go ahead.
So I will go first. So can you go to the slides that shows the Google search results for the coronavirus?
Google search result for coronavirus. And these few slices basically related to that.
Yes, exactly this one. So here I'm having a question that for both the coronavirus and the fever, we can say that there exists almost two peaks in each figure. And we show the first peak is small, while the second peak is large. So is there any insight reasons of why there usually exists two peaks, and first a small one and a larger one?
I think you mean this peak is larger than this peak?
No. So if you go to the figures that on the right one that you are picking now.
This one?
Yes. We can usually say
this
two peaks.
Oh, okay.
Yes.
This is probably influenza type A or type B, and this is coronavirus. Okay. That's why I said data is so confounded, because this is search volume for cough, and the flu symptom also have cough.
Yeah. Okay, I understand.
Well, actually, this is a huge research issues for right now. Right now, the flu is going to pick up. Trying to identify who gets flu and who gets COVID is a challenge.
Yes. So my question is why they are all showing similar patterns, that first a small peak and then a larger peak.
Yeah, it's one flu, one COVID. And you know what I was also suspecting? Right here, this peak can actually be that large, meaning that the under-reporting and the testing capacity back in March, it's just, the actual cases is much higher. Like what I showed in my other paper, is probably should be 10 times bigger in this spike. That's why, relatively, I truly believe that the spike in March, the new cases in March, is much larger than the new cases in the July, although in the confirmed cases, it's the other way around. So another very big challenge is that you have no access to ground truth. I have a paper that talk about, it's probably March is probably 10 times the one what it is reported, but I have to have a leap of faith or have to convince others to really trust me on this before I say, my result is actually accurate, because it doesn't really agree with the confirmed cases. So there are also, how do you actually convince people that without a ground access to a ground truth, that we are doing the data is actually right, the confirmed cases is wrong. It could well be that, but it's a very it's confounded.
Okay, I understand. Thanks.
Yeah. So there was one more, and then Alex, you can go ahead. One question on the chat by D Wu, who asks how to predict. Yeah, you can read it, I guess. Shihao. How to predict if it will become an epidemic?
Sorry. Can you repeat again? What is the question in the chat?
Yeah, the question is how to predict if it will become an epidemic or not. 1 week ahead is good, but may not interest me a lot until it can impact my normal life. Divu. So D, if you're online, you can ask if I have missed anything. So basically, can you do further more than 1 week? I guess that's the question.
Oh, we can do 2 weeks. Right now, we can do 2 weeks. 3-4 weeks is a stretch, and I can give you a number for 5 weeks, but it's just something that I wouldn't even believe in. And I think it's shortcomings of data-driven approaches where a lot of signal that I use is going to be short-term signal because I do not have a model for the mechanistics of the disease. So a current work I'm trying to do is, in the SIR model, you have mechanistics of the diseases where you have DR, DT, DS, DT, and all that to be a proposed functions, pretty much like a parametric approach where you have some parameter that specify the form. So right now we are trying to do is, okay, can we still use that for the part we really believe that the interaction should behave like this? Let's use the parametric approaches. And for the part we don't really know how things that interact or what's the functional form, is that going to be a product or that? Can we learn it from data? So it's kind of semi-parametric in a way that the ODE system, the dynamic system, is half specified and half to be a function f, where the f can be represented, I don't know, like a regression, or somebody is trying a neural net, some type of kind of non-parametric approaches. The idea is really trying to bridge data-driven, the school of thoughts in the data-driven way and the school of thoughts in the SER way, because you normally see the two schools to be very distinct from each other, but they are because data science way is very good in terms of short-term predictions because it uses alternative data. SER mechanistic way is good at long-term. They can give a reasonable number, believable number for 6 months. My model will not give a believable number for 6 months. So, if we can...
That's what I was... we were talking about some predictions for coronavirus 6 months in the future, right? So it's hard to say how much to believe such predictions, right? So good. So Alex, you had another question, right? And then there is another question on the chat. I'll go over that later.
Hello,
Alex?
Professor. Yes, can you hear me? Yes. Thank you for the presentation. It was very insightful. I have two quick questions. One is I think your models are county level models. However, you also are incorporating demographics. That's what I heard.
Yep.
So I'm not sure how you are doing that. If you are constructing one model per county, how you are learning the effect of demographics.
Model. The demographics is available, I think. Some of it may be available only at the state level. Then if the demographics are available at state level, that's fine. We project the state level to be a kind of a shared factor in a regression across all different counties in that particular state. So it's like a multi-task regression, or you call it, you just have 3,000 response, then you are trying to predict 3,000 responses using a spatial regression approach.
Okay. My second question is that you mentioned that the connectivity between counties was being constructed based on a transportation network. So I wonder that, for example, this is just a curiosity of how you are constructing this network. Is it that how many highways there are between the two counties, or
if there are no counties that directly neighboring to each other, I construct their spatial coefficients to be 0. So think about spatial regression as multiply a matrix on top of the vector of 3,000, right? It's a 3,000 times 3,000 matrix, and I only allow non-zero elements if there is a highway connections, if there is a kind of flight connections, and so on.
Okay. So 0, 1 is not...
Go ahead.
It's a binary. It's
binary,
either it's connected or not. Okay, got it. Thank you.
It's either 0 or not. So that's why I said I use that structure as a baseline and learn it from the data.
Okay, great. Thank you.
Rogelio, you had another question, right? Do you want to just go ahead and ask instead of me trying to repeat it from the chat?
Yeah, sure. So, I was wondering if for the queries that you're using to your model, if you could select for combined searches, for example, a person that could look for coronavirus plus the symptoms plus some medicine, compared to a person that just look for coronavirus alone. If that combination of queries can help you to distinguish between a possible infected individual and another that is not.
Good point. So we have both. There are query terms that have to be exact, like coronavirus. And there are also, for example, the search queries for coronavirus, and they're also called topic. For example, I'll give like the president of the United States and Donald Trump is the same search. So there are in the natural language processing, there are existing topics that is predefined that is probably a hex string that defines the same entity with different phrasing of it. So we are already using topics like that in our data, and sometimes also the coronavirus, for example, or the fever. Google will return the queries that have fever as one particular word in your entire search string.
Okay.
So to further clarify Rogelio's point, should we think that you're really looking at a set of phrases, set of terms, rather than just a single term, right?
Correct. Because when Google returned the search volume for fever, they actually returning all the searches, the total volume of searches that is related to fever divided by the total volume. Actually, the way they do it is by sampling from their search log. And if their search log have a fever, irregular expression of fever in their in the phrases you search, it has a +1, and then you look at the ratio of this. And they are using a sampling-based approach so that every time you are getting it, you are getting a slightly different result. And it also is a differentially private mechanism so that it ensures that the data we got is going to be have preserved the privacy. So there are more mechanistics behind what's the search volume, but I just didn't really touch upon that right here.
Great. And a final question, I guess, for the students, given that they are doing projects also which may use such query data, so how should they go about getting them? Is it just an API Google gives you, or
go to trends.google.com? You guys have my share screen, right? Let's just go to trends.google.com and coronavirus and download data.
That's it. Yep. So yeah, I know there are a lot of people who are doing projects which are trying to use different data sets. So this is a good way to get it.
It's very simple. You can do past 6 months. You can do past 7 days. It'll give you hourly data, but it's not very useful because no hour doesn't carry etymology meanings. You have 90 days, and you can compare coronavirus with the fever. Probably is going to, so there are things you can do.
Yep, cool.
What are the y-axis values?
Yeah.
Sorry?
What are the y-axis values?
The relative search volume. So it will be normalizing by the highest value to be always 100. And I really, if you're going to use this data, please read the README. Okay, the Google actually have a very comprehensive doc on their help file on about the Google Trends, what it is, and all that. If you're doing data science, you have to understand your data first before using it.
Yep. Great. Thanks a lot, Shah. That was a very nice talk, and I think I'm sure it was very helpful for all the students to hear about this too. Great. Thank you again. And feel free to reach out to Dr. Yang if you have any questions you want to talk further. Right. And great. Thanks, Shah.
Thank you.
Thank you.
Yeah. Thanks everyone. Bye.
Bye.
So, and for the students, your homework is out, so you should check it out. Homework too. Bye.
Bye.